Hello everybody. In this video we're going to discuss the third topic of chapter 4, formula mass. Well, we'll discuss how we calculate the formula mass for compounds according to their formulas, and then we'll talk about how we calculate the mass percent, and then how we come up with the formula based on the experimental mass percent data. Okay, let's take a look at this example. How do we calculate formula mass? Well, in our textbook we used formula mass, but in some other textbooks you can also see formula weight, molecular weight, or molecular mass. These four phrases are pretty much the same. Okay, so don't get surprised if you see some other phrases in other when we do practice, or or when I say it. Anyway, so how do we calculate the formula mass based on the formulas of compounds? Here is the equation for us to use. Number of the atom of the first element in chemical formula times the atomic mass of first element plus the number of the atom of the second element times the atomic mass of the second element, and so on. Okay, if you have third element, then you do the same thing. Well, before we talk about those calculation example, we have to understand what we are trying to do. Remember, when we talk about the atomic mass, we did some practice between unit conversion practice between the mass of elements and the mole number of the elements. Okay, so this is what we did, and between these two, the bridge is the atomic mass of the element. Okay, the unit is gram per mole or AMU. It's up to you which one you want to use. Anyway, so in this conversion, we use atomic mass to identify either the mass of the elements or the mole number of the elements if you know the other one. Okay, same reason here. Okay, same purpose. If we know the formula mass, then we can find out the mole number of the compound, or we can find out the mass. Okay, let me write it here. So the mass of a compound and the mole number of the compound okay, between these two, the bridge is the formula mass, okay, or formula weights, or okay. Again, this one here is gram per mole. In other words, formula mass is the unit conversion factor for us to identify either the mass of a compound or the mole number of a compound if you know the other one. Okay, let's use the following two questions as examples to demonstrate what I'm trying to say here. Okay, determine the mass, determine the mole number of the molecules for each sample. Okay, this is what we need to do. The first compound is the CHCl3. You have mass data available. We need to find out the mole number. Okay, the mole number of the CHCl3 if we know the mass of CHCl3. Well, first thing is, in order to do the unit conversion, or the conversion, we need to find out the formula mass of CHCl3. So let's do that. Okay, according to our equation right here, let's start from carbon, first element. Okay, so the formula weight or formula mass equals to 1 carbon times the atomic mass of carbon, okay, which can be identified from a periodic table. That should be 12.01 AMU. Okay. And the second element, hydrogen. So we go to the second part. Remember, between the two parts, it's plus. Okay. That's why I have plus here. Okay. Now 1 hydrogen times the atomic mass of hydrogen, that is 1.008 AMU. All right, third element, chlorine. You have 3 chlorine. Remember, the number on the lower right corner of an element in the formula represents how many atoms you have for this element in this formula or in this compound. Okay. Well, since you have 3 chlorine, that will be 3 chlorine times the atomic mass of chlorine, that is 35.45 gram per mole. Okay. If you do the calculation, you will get the formula weight or formula mass for CHCl3 as 119.368 gram per mole, which is also AMU. Okay. Well, let me write the whole thing. Okay, just in case. So AMU, that equals to 119.368 gram per mole. Okay. Of course, in order to be consistent, let's write the AMU here. Okay. Oh, well, some of you may ask, hey, what's the significant figures that we should have? Well, when you calculate the formula weight or formula mass, because these numbers, they are from periodic table and also formula, they can be considered as constant. Therefore, you don't have to worry about the significant figures. Okay, but you do need to consider the significant figures of this data because it's from measurements. All right, now this is the first step, formula weight or formula mass of CHCl3. Now the second step is to convert the mass of CHCl3 to mole number of the CHCl3. So you have to use the mass, 88.65 gram times, okay, it's time for us to use formula weight. Well, since we want to cancel the gram, so we should have 119.368 gram at the bottom and 1 mole on top. Okay, and if you do the calculation, that will give you 0.7427 mole. Okay, 4 significant figures. This is the first example. Now the second example, we just follow the same procedures. Okay, but in this example, I want you to be careful about the number of the atoms for each element. Okay, let's start. Step 1, formula weight or formula mass equals to first element copper, 1 copper times the atomic mass of copper, 63.546 AMU, plus, well, now it's nitrogen. Well, as you notice that NO2 is a polyatomic ion, if you happen to remember, okay? And each NO2 has 1 nitrogen, but in this compound, you have 2 NO2. Therefore, you have 2 nitrogen. So essentially it would be 1 here times 2 equals to 2. All right, so that's how we come up with the 2 nitrogen. For a nitrogen, atomic mass is 14.01 AMU. Okay, and then third element, oxygen. Now again, each NO2 has 2 oxygens. Since you have 2 NO2, therefore you need to consider both NO2 when you count how many oxygens you have. So 2 times 2 equals to 4. Therefore, you have 4 oxygen. For each oxygen, atomic mass is 16.00 AMU. Okay, so if you do the calculation, it's 155.566 AMU. Let me just write it here. So that equals to 155.566 gram per mole. You can use gram per mole directly. Okay. All right. Second step, convert the mass of copper nitride to the mole number. Well, remember this is a kilogram. Okay, be careful. So we have to convert that to gram first. Kilogram times, well, since we want to cancel kilogram and keep the gram on top, and if you happen to remember, okay, kilogram lowercase k represents 1000, 10 to the third. Okay, and then we use formula mass of copper nitride. So that should be, since we want to cancel gram, so 155.566 gram, 1 mole on top. Okay, so you can cancel the kilogram here, and you can cancel the gram here. So the final unit would be mole. And if you do the calculation, it's 151.60 mole. Now let's consider significant figures, because this one has 3 significant figures. We should have 3 significant figures for the final answer, which should be here. And if you drop the tail, you will get 152 mole. But as we mentioned in chapter E, this is ambiguous. Okay, this is ambiguous. Therefore, we need to use scientific notation 10 to the second mole. So this is the how we calculate the formula mass and how we use formula mass to help us identify the mole number of a compound. And of course, if I give you the mole number of a compound, and I expect you know how to convert the mole number of the compound to the mass of compound. Okay. Again, you need to use the formula mass. All right. Next slide is about the composition of a compound. Okay. If you know a formula for a compound, then based on the formula, you should be able to calculate the mass percent of the element in the compound. Okay. We'll talk about why we want to consider this part in the next slide. Okay. All right. Here, mass percent can be represented by capital X. Okay. And that equals to the mass of the elements X. X could be any element in the formula. In 1 mole of a compound divided by the mass of 1 mole of compound and times 100%. Well, when you look at this mass percent equation or formula, it's a little bit confusing. So let me write another form of this equation. So I do believe this one is going to be easier. Okay, so that equals to X mass percent of a certain element. That equals to number of atoms times atomic mass of the atom, atomic mass, okay, divided by the formula mass of the compound. Of course, on the tail, let me start another line, times 100%. Okay, so I think this one is easier. Let's see how. 2 questions. Calculate the mass percent of nitrogen in each compound. Magnesium nitride. Well, you have 2 nitride in this formula. If we want to find out the mass percent of nitrogen, let's see how do we use this equation. Okay, so the mass percent of nitrogen, that equals to number of the nitrogen, that it will be 2, times the atomic mass of nitrogen, that is going to be 14.01 AMU or gram per mole, okay, divided by the formula mass of Mg3N2. Okay, so at the bottom, we need to do what we did on the last slide. 3 magnesium, each magnesium atomic mass is 24.30, my bad. 30 AMU plus, okay. Again, you have 2 nitrogen, so when you calculate the formula mass of magnesium nitride, this 2 nitrogen has to be considered. 14.01 AMU times 100%. Okay, all right, now on top, let me write one more step, is 28.01 AMU. At the bottom, if you calculate, that's going to give you 100.92 AMU. Again, please remember, we don't have any measurement from this for this equation. Okay, everything is the constant. So essentially, you don't need to worry about the significant figures. Okay, but if you really want to practice what the significant figures are, we can just follow, just assume this is pure math. Okay, all right, so that means that you have 2 significant figures here, or 4 significant figures here, and then you would have 2 decimal places because this is plus. Okay, but anyway, the last calculation step will give you 27.76%. 4 significant figures because you have 4. Again, like I said, you don't need to worry about the significant figures when you calculate the mass percent of an element according to the formula of the compound. Okay, now let's see example B. Now example B is a little bit complicated because you have more nitrogen atoms in this formula. Well, when you look at this, you have 3 nitrogens here, right? And you have an H2 group in this formula, and you have 3 NH2 groups. Therefore, you need to consider all of the nitrogen from those 3 NH2 groups. Okay, so 3 nitrogens here, 3 nitrogens here, so you have 6 nitrogens total, right? So the X equals to 6 nitrogen. I'll write it here on top. You don't have to write the N here, okay? I wrote it here because I want to show you what I'm trying to do. So 6 nitrogen times the 14.01 atomic mass of nitrogen. I'll use gram per mole, okay? It's the same thing as AMU. Now at the bottom, carbon, you have 3 carbons, okay? So 3 times, for each carbon, it's 12.01 gram per mole plus, okay? Now nitrogen, you have, as we did on top, 6 nitrogen times 14.01 gram per mole. Okay. Well, you still have the third element, that is hydrogen. Each NH2 group has 2 hydrogen, you have 3 NH2 group. Therefore, 2 times 3. So total you have 6 hydrogen, okay, plus 6 hydrogen times 1.008 gram per mole. Oh, okay. Well, of course, you need to multiply 100% at the end. All right, and then if you do the calculation, on top you have 84.06 gram per mole. At the bottom, you have 126.138 gram per mole. Okay, we're supposed to have 2 decimal places times 100%. And if you do the calculation, final result is 66.64%. 4 significant figures, because this one has 4 significant figures. All right, this is the mass percent composition of a compound based on the formula. Now, go back to the question I asked before we started the discussion here. Okay, why do we care about the mass percent? Because if you know the formula of a compound, you can calculate the mass percent of the composition, mass percent composition of the elements, each element, right? You just follow what we just did. But remember, in chemistry, one of the most important tasks in chemistry is to synthesize new compounds. So, see, you in lab, you just synthesized a brand new compound, and that might give you, help you, get Nobel Prize. Of course, you want to know what the formula is, right, for this new compound, because nobody knows what that is, and you are the first one. So you want to identify the chemical formula. How do we do it? Well, if you can do experiments to find out the mass percent of each element in this compound, then mathematically you can come up with some ideas about the chemical formula of this new compound. That's what we are going to do in the next 2 slides. Okay, so the experiment that we need to do is elemental analysis right here. So you just need to do experiment, identify the mass percent of each element in this compound. Here, this is a very simplified picture to show you the mechanism of elemental analysis. Basically, you have your compound in this tiny box, a chamber, and then you heat it up. Meanwhile, you blow air or oxygen into this chamber, let this compound burn in oxygen, and then it depends on what element you have in this compound, different product will be generated. If your compound has nitrogen, okay, has hydrogen, it will generate water, because hydrogen will bind with oxygen, generate water, and water will be absorbed by magnesium sulfate. So you can see the mass change. Okay, and if your compound has carbon in it, carbon will bind with oxygen to generate carbon dioxide. Again, this carbon dioxide will be absorbed by sodium hydroxide, so you will detect the mass change again. Okay. If your compound has nitrogen, then nitrogen will bind with the oxygen from air to generate nitrogen oxide. Again, you have some certain methods to trap the nitrogen oxide generated, and then you can identify the mass change. By having the mass change for the different elements, okay, computer can help you identify the mass percent of each element. Okay, and then based on that data, you can calculate the formula, get some ideas, empirical formula at least. So that's always a good starting point if you want to get more ideas about what the compound is. Okay, so let's do a quick practice and see how we identify the formula or empirical formula. Well, in this question, elemental analysis tells you the mass percent composition of 3 elements in one compound. Here, these are the data. Determine the empirical formula of this compound. Remember, elemental analysis has its limitation. Sometimes you may not be able to identify the molecular formula, but you can identify the empirical formula, and based on that, you can do more experiments and find out the actual formula. Okay. Remember, empirical formula is the formula that indicates the smallest integer ratio, smallest positive integer ratio of the atom of the atoms in a compound. Okay, so keep that in your mind. Now, how should we start? Well, the first step is, remember, these are mass percents. Okay, and it's for instance, beryllium 858%. So a very good starting point is you can assume that we have 100 grams of this compound. Okay, so let me write it down here. Step 1, assume 100 grams of this compound. Okay, now this is a very good starting point, because if you have 100 grams of this compound, then the mass of each element can be calculated based on their mass percent composition. For instance, okay, let's calculate the second step. Calculate the mass of each element. For beryllium, that will be 100 grams times 85.8%. Okay, so that will give you 8.58 grams beryllium. For sulfur, 100 grams times 30.48% equals to 30.48 grams of sulfur. For oxygen, 100 grams times 60.93%, that equals to 60.93 grams. Okay, now what's next? Well, the next thing is to identify the mole number of each element, and then find out the molar ratio among elements to identify the empirical formula. All right, so step number 3, mole number of each element. Okay, for beryllium, the mole number equals to the mass. Okay, remember what we did when we talk about the mole number of the elements. We need to use the atomic mass as a bridge, right? And you have the mass information right here. So 8.58 grams times atomic mass of beryllium. How do we use it? For the atomic mass of beryllium, it's 9.012 grams per mole. Since we want to cancel gram and keep the mole, so 9.012 grams. Let me write it here. Okay, so this is how much beryllium you have. And for beryllium, the molar mass, atomic mass is 9.012 grams. Beryllium is 1 mole of beryllium. Okay, so it will give you 0.9520 mole. Okay, we're supposed to have 3 significant figures here. For sulfur, you have 30.48 grams of sulfur. Again, use the atomic mass of sulfur to convert that to mole number. Sulfur atomic mass is 32.066 gram. Sulfur, it's 1 more sulfur. That equals to 0.95054 mole. Okay, we're supposed to have 4 significant figures. Oxygen, you have 6.93 gram of oxygen. Convert that to the mole number of oxygen. Atomic mass for oxygen 16.00 gram. Oxygen is 1 mole of oxygen, so that will give you 3.8081 mole. 4 significant figures. Okay. Now the next thing is we are getting closer and closer. Now the next thing is to identify the molar ratio among those elements. Okay, so that will tells us the smallest integer, positive integer ratio. Well, now you have 3 mole numbers. How do we find out the molar ratio? We use the smallest mole number as a standard to normalize the other mole numbers. Okay, what do I mean by that? Okay, let's see. Sulfur, it has the smallest mole number among the 3 elements. Okay, so I use sulfur, the mole number of sulfur as a standard. So sulfur itself, how do we normalize it? You just use the mole number of each element divided by the smallest mole number of the element. Okay, so for sulfur, it would be 0.95054 divided by 0.95054 itself. So that equals to 1. For beryllium, okay, remember we use the mole number of sulfur as a standard. Okay, so when we normalize beryllium, we use the mole number of beryllium, 9520 mole, divided by the mole number of sulfur, 0.95054 mole. That equals to 1.00154 ratio. Okay, now as you notice that this number is very, very close to 1. And we know that in order to come up with the formula, you have to find out the smallest positive integer ratio. So we have to keep an integer ratio based on this number. Since this is very close to 1, you can drop all of the tail behind the decimal points. So roughly this is going to be 1. We do the same thing for oxygen. For oxygen, okay, you use the mole number of the oxygen, 3. Let me delete this. Okay, so for oxygen, 3.8081 mole divided by the mole number of sulfur, 0.95054 mole. Okay, that equals to 4.006. And since this number is very close to 4, and we should keep an integer, so we drop the tail behind the decimal point, so that would be 4. All right, now we got the molar ratio 1:124, and so it looks like this is going to be beryllium SO4. Okay, and if you are familiar with the cations and the polyatomic ion, this actually would be beryllium sulfate. Okay, so this is the basic procedures of this question. Okay, how we identify a empirical formula based on the mass percent composition of the elements in the formula, in the compound. Okay, let me know if you have any questions.